Today we are aiming for zero. I know, just let that sink in for a minute. It's not something you hear all the time, right? How can I get absolutely nothing? You certainly don't want to hear that at a baseball game. And a basketball game? Eek! What have you been doing for the last 48 minutes? But today, the zero we're talking about is emissions. The electric car revolution is here, my friends, and we need it to be, especially if we're going to keep pace with the global regulations set into place in the next couple of years. And, well, if we really want to go 0 to 60 in this electric race, we better start talking about battery management systems, voltage isolation, and a whole lot of circuit protection. You on board? All right, better get that seatbelt on tight, my friends. We're just getting started. Hi, I'm Amelia Dalton, host of Chalk Talk. Yes, we are talking about all the bells, whistles, and knobs, or would that be inductors, converters, and diodes, you will need to get rolling in your next electric car design. With Cathal Sheehan from Bourns joining me in the front seat, we're headed to zero. You coming with us? And before we get started, don't forget to click that link. There you can find even more information about this topic from Bourns. Hi, Cathal. Thank you so much for joining me.
Oh, thank you very much, Amelia. It's a pleasure to be here.
Okay, so before we dive into the nerdy details of batteries and BMSs and so forth, let's talk a little bit about why we are all here designing electric cars in the first place.
Well, if you look at typical gasoline-powered engines and the emissions that they emit, it's really impossible for them to meet the new legislation guidelines, whether it's in Europe or the US. It's just not possible to meet that. The only technologies that can possibly meet those guidelines are hybrid electric vehicles or battery electric vehicles. And in fact, it is envisaged that in some European countries, in cities, there's going to be zero emissions targets. So the only way of being able to meet those targets is on a battery electric vehicle.
Yeah, zero is very difficult to meet. And what if we need a component that's not exactly the specs of what you offer? Is there any way to order off the menu or get some custom help?
Absolutely. Bourns has a team of electrical, mechanical, and process engineers that can take a specification and create a concept drawing in SolidWorks and can write a quotation. And if that quotation is acceptable, they can make samples using 3D printing technology in a very, very short period of time. And before that, of course, they would use the simulation tools like ANSYS, for example, to make sure that the design meets all specifications. Then they would make samples and test them. It could be a transformer for a switch, a full-bridged dual-active converter, or a resonant LLC converter, or it could be for a PFC choke on an onboard charger. Absolutely.
So, as we're migrating from internal combustion to EVs, we're kind of going at it one step at a time, aren't we? Tell me a little bit about the various types of electric vehicles.
This slide just shows, kind of categorizes the different types of vehicles that are out there on the market at the moment. The first one is the mild hybrid electric vehicle, and that's using a 48 volt technology, typically around 3 kilowatts. And that's used to power things like the air conditioning or the start stop function of the motor. And in the future, in fact, it will even be able to help the powertrain. So that's 48 volt technology. Then the hybrid electric vehicles and plug-in hybrid electric vehicles, they are operating at 400 volts technology. And the reason for it's such a higher voltage is if you're trying to drive a motor, you're talking about 25 to 30 or even more kilowatts. Typically, the current that's driving those motors can't be more than 250 amps. So you have to increase the voltage to reach those power limits.
Otherwise, we would need enormous cables, right?
Exactly. And finally, some of the battery electric vehicles are now migrating towards 800 volts again, as the power goes up, as we head towards 100 kilowatts and more. The key components in the electric vehicle that we would be looking at, and for the designers, would be the DC-DC converter, the battery itself, and then the inverter and motor drive.
Okay, great. So, looking at those various types of electric vehicles, how does that translate into what companies are building today?
Well, in fact, there have been announcements by all of the major OEMs that they are moving towards full electrification of their vehicles. And this chart just shows the predicted production levels in millions of units of the main technologies. And this is based on announcements from the different OEMs on new models that they're going to be releasing. You can see in 2025, for example, there will be 27 million electric vehicles shipped, and almost half of those will be 48-volt systems. And then the rest will be plug-in and full hybrid vehicles, and then finally, full battery electric vehicles.
Wow, that's a lot of new electric vehicles on the road. Now, let's start the engineering nuts and bolts. It seems to me that the critical thing in EV development is the battery technology and controlling that battery technology, right? What kind of batteries are people using in EVs?
The battery is really at the heart of the electric vehicle. And what you want is an energy source which has the maximum energy density so that you can make the battery as small as possible. And currently, the only real technology used at the moment for battery chemistry is lithium ion. That has a specific energy of between 80 and 160 watt hours per kilogram. Now, typically, a battery pack will be composed of different individual cells, and the cell voltage will vary depending on the chemistry used, depending on the anode and the cathode used. It will vary between 2.5 to 3.5 volts. Depending on the chemistry used, then a pack will be constructed with strings of cells. Some of them will be in parallel, and they will be put into battery modules. And cascading those in series, you are able to produce the voltage required. So, for example, the Nissan Leaf from 2011, that has 192 cells, giving us a total output voltage of 360 volts. And that's divided into 48 different modules. And the battery capacity of that then is 24 kilowatt hours.
Cool. So it takes a lot of those 3.8s in series to get up to 360 volts, right?
Absolutely, absolutely. But the pack itself really depends on the application. For example, does it need a very high charge capacity? You might choose a different anode, for example, or cathode. It might be an LTO cathode or a graphite. Very much depends on the application.
With that much energy, there must be a lot of heat generated. Is temperature an issue with this kind of battery technology?
Yes, absolutely. Lithium ion batteries do have quite a limited operating temperature range between 20 degrees and 35 degrees. Therefore, the temperature of those batteries is quite critical. If the temperature goes too low, heading towards 0 degrees, the internal resistance in the battery will increase, which reduces its power delivery capability. And on the other hand, if the temperature gets too hot, if it gets towards 50 degrees, the battery starts to degrade. So the overall life of the battery will decrease. So the temperature is critical. And in fact, keeping that temperature under control is a key factor in electric vehicles.
Got it. That's because the batteries have a smaller temperature range than the vehicle themselves, right?
Yeah, they're like humans. We're only comfortable in a certain temperature range. After that, we need to take protective measures.
Okay, and so now let's head down that same path. Let's discuss how much we manage those batteries. That can get fairly complex, right? We have to keep temperature and voltage and so forth under control.
Yeah, exactly. I mean, to keep that under control, we need what's known as a battery management system. It's a circuit. Its main function is to measure three variables: voltage of the cells, the current going through the battery or going out of the battery, and then the temperature of the pack. So, by using the voltage measurement function, it's able to check the state of charge of each cell, which is a key parameter in making sure the cell is not overcharged or undercharged. It also is able to do some battery balancing. If one cell is too far overcharged and the other cells are undercharged, the life storage capability of the pack is decreased. So doing battery balancing is important as well. So therefore, a battery management system would consist of a battery management IC, which can do all of those functions, measure the voltage, the temperature, the current, and then it also communicates this data to the central engine management unit of the car so that it can take protective measures if necessary. So basically, the battery management system is a key function in the overall electric vehicle.
Now, I hadn't thought about balancing before, but in those long strings of a series of cells, it seems like one cell down there could get low and could cause a whole bunch of bad problems.
Exactly. In fact, mostly there will be a series of resistors and MOSFETs placed around each cell. And if one cell is too far charged, it's bypassed by the MOSFET and the resistor, allowing the other cells to continue to be charged. And then when they all reach the same level, then the cell is reconnected to the rest of the pack.
Got it. Okay. Now, with the voltage of the batteries being so high and the voltages we're using in our system being so much lower, how do we maintain isolation between the high voltage in the batteries and the rest of our system?
Yeah, in fact, in a pack, if you're in a battery electric vehicle, you could be talking about 400 volts, which is hazardous. And we don't want that voltage jumping across from the pack into other areas of the car. So there has to be isolation. And the most common method of isolation is using a transformer with a high working voltage. And the most common location for the transformer is placed on the communication bus in the battery management system. Typically, you will have several of the battery monitor ICs in a daisy chain, and they communicate with each other through this communication bus, an isolated communication bus. The most common one used is SPI. It's a two-wire bus, and the name for that is ISO SPI. And those transformers will relay the critical information, voltage, current, and temperature to each IC and back over to the central engine management unit. And because these transformers are relating critical data, they need to be tested and approved by the manufacturer of the monitor IC before the OEM can use them, because they're such a critical part of the battery management system.
That seems really important. One of the places I particularly don't want to see these voltages migrating to is inside the passenger compartment.
Exactly. That is always a risk that you want to avoid. So those transformers need to have high isolation, and they need to be certified and approved by the IC manufacturer.
Okay, so let's talk specifically about what kind of transformers you guys offer.
So Bourns have developed two models at the moment. We have a two-channel transformer that's useful for a daisy chain where maybe you're in the middle of a daisy chain, so you've got one IC, you're kind of in the middle, so you're transferring data into the IC and out of the IC. So that would require two channels. And then we have a single channel transformer that can be used as a smaller pack where it has a lower voltage, or it could be used at the very end of a daisy chain where you don't need to pass the data any further.
So to terminate it?
Terminate it, exactly. And those parts, they are both rated to 1600 volts DC. They both can withstand 4 kilovolts of high pot. They are fully approved to AECQ 200 stress tests. They are manufactured as well in a IATF approved facility, which has been VDA 6.3 audited. And they are tested and approved by ADI with their LTC 68, 10, 11, 12, 13 battery monitors and their 6820 ISO SPI transceiver.
Okay, so to shift gears here a little bit. Now, since we don't have a gas tank anymore, we need something fancier than a float in a tank to tell us how much energy we've got left in the batteries and what's going on in the state of the charge, right? How exactly do we accomplish that?
Yeah, exactly. We don't have a float anymore, which can tell us how much fuel is left in the tank. We need to use the battery management system to tell us that. And the battery management system we rely on a current sensor. And the current sensor has to measure the battery in various conditions. When you're charging the battery, for example, so at the very start of a charging cycle, it might have to carry quite a lot of current if the battery is empty. And towards the end of the charging cycle, it has to be able to measure low levels of current. Similarly, during discharge, when it's driving the motor, it needs to be able to measure currents during acceleration, for example, and also when the motor is stopped. So it has to have quite a wide range and quite a high accuracy. And measuring the current is fundamental for the battery management system to make sure the battery is okay, that it's not charging too quickly, for example, which could degrade the life of the battery. The most common method, especially in 48-volt packs for measuring current, is using a shunt-based system. And the shunt-based system consists of a current sensor would be a bus bar type resistor, which would be attached to the bus bar using a series of screws and washers. And this sensor would be able to carry anything up to steady state currents of 300 amps, maybe for a short period of time, 1000 amps. These resistors have a very low resistance value, maybe 50 microohms, for example, which is very low. And therefore, the voltage developed across those resistors at, say, peak currents would be only about 50 millivolts. 1000 amps across 50 microohms using Ohm's law, that's 50 millivolts. So you need a current sense amplifier with a very low offset and a high common mode voltage, which can translate that 50 millivolts into a large enough signal for a high resolution analog to digital converter, like a sigma delta converter, for example, to be able to accurately read that. Therefore, a kind of a shunt type module is attached to the top of the shunt that can be reflowed onto the tin plating on the shunt, or it can be attached via a series of washers and standoffs, and then via a connector to the battery management system.
Now, it seems like the critical component here would be the current sensor. Now, what does Bourns have in the realm of current sensing?
Bourns has a series of busbar type shunt resistors called a CSM 2F series. These shunts are designed to carry anything up to 1000 amps of current. Now, these shunts are basically, there's a copper terminals, and in the middle then there is a very fine resistor alloy with a very low resistance and temperature coefficient of value. And these devices are very good because, essentially they are resistors. And by passing the current through the resistor using Ohm's law, you can very accurately calculate the value of current going through the shunt by just measuring the voltage across it. Now, using the current sense amplifier and A to D converter that we mentioned earlier, it's possible to get a very accurate signal. First of all, if in the factory you can calibrate this using a known current, measuring the voltage across that shunt and recording that value, you know then exactly the exact resistance of the shunt, so that when that goes into the field, then the circuit knows exactly the resistance. So that allows you to get a very accurate calculation of the current. And also the temperature dependence, the TCR of these resistors is very low. It's 50 ppm per degree centigrade. However, it's possible the factory can provide a lookup table showing the resistance drift over temperature. And this lookup table is stored in the battery management unit to compensate for increases in resistance as the temperature increases. These devices will generate power between 36 and 50 watts depending on the current. And as they generate power, the temperature goes up on the resistor, and so the resistor also goes up. But by using this lookup table, it's possible to compensate for that and maintain the accuracy of your current measurement. And we have gotten accuracies down to 0.1% across a full current range. So accuracy is very, very good with these shunt resistors. It's one of the reasons why they are a very common choice now in battery management systems. And these shunts are produced in a IATF automotive-proof facility, and they are all AEC Q200 appliance.
Cool. So they can even compensate for the self-heating that happens when they're under high loads?
Absolutely.
Now, does the BMS have other functions as well? What about current protection?
Yes, absolutely. So a battery is a high energy source. And if there is a short circuit or some sort of an event like an accident, it can be very hazardous indeed. The battery management system has the task of disconnecting the battery from the rest of the system in the event of an emergency. Typically, they will use either a contact relay to do that, which can open in a certain period of time. This process during a short circuit will see very high currents rushing out of the battery, which could damage the rest of the battery management system. You're talking about, it could be anything up to 1000 amps in a very short period of time. Now, the contact relay is able to handle those types of currents, but nevertheless, there is what's known as a flyback voltage developed during this time as a result of the sudden decrease in the massive currents generated by the short. Now, in 48 volt systems, there is a trend towards what's known as a smart switch, which is a series of MOSFETs, high current MOSFETs. And these MOSFETs are a lot faster than a relay, and therefore the short circuit current is a lot shorter and a lot smaller, which is safer. However, there is still a flyback voltage developed across the drain of the MOSFET, and that flyback voltage can damage the drain of the MOSFET. And therefore, it's necessary to clamp that flyback voltage during the short circuit process. Typically, the standard now for 48 volt vehicles, for example, is to make sure the voltage never exceeds 60 volts. So typically you would use a 3 kilowatt or a 5 kilowatt TVS diode there that can handle the energy and will clamp with a very low dynamic resistance. So it clamps the voltage. It goes from 48 volts and it makes sure that it doesn't get higher than 60 volts during that short circuit period. So high power TVS diodes are important for these types of systems for safety.
So I assume that in a car, it's pretty noisy and the environment is pretty chaotic with current and voltage spikes, with all the stopping and starting and accelerating, especially the way I drive. How do we keep those transients down?
The battery itself is monitored by battery monitor IC, and the battery monitor IC uses an A to D converter to measure the voltage across those cells. Transients can very easily happen on the battery side, and those transients would be too much energy for the A to D converter. Typically, the battery management ICs have internal Zener diodes, which can handle a certain amount of energy. But if the energy gets too much, which could happen in the event of maybe a battery string being disconnected suddenly, it would punch through the Zener diodes and destroy the battery management IC. And in that case, you need kind of a very fast overcurrent protection in series with the battery monitor IC. Those types of very fast overcurrent protectors can prevent damage occurring to the internal protection circuitry of the battery monitors.
Okay, let's talk about those diodes. What kind of diodes does Bourns offer?
Bourns has a range of TVS diodes which are AEC-Q 101 compliant. Some of the diodes are in SMA packages, SMB packages, SMC packages, which are well-known industry standards. And for protecting the switch or the smart switch from flyback pulses during short circuits, we would recommend our 5.0 SMDJ Q series TVS diode. That's rated to 5 kilowatts of transient power.
And what about for overcurrent protection?
And for overcurrent protection, Bourns has a range again of AEC-Q 200 compliant products, be they polymer PTCs or multi-fuse series, which are used in a variety of areas like USB port protection, for example. USB ports are also used in vehicles and battery management system boards. But for protecting the battery monitor ICs from transients, we would recommend our ultra high speed silicon protector. It's called the TBU-DB055-100-WHQ. And that is a very fast overcurrent protector. Between start to finish, it will cut current off in less than a microsecond.
Oh, wow. I'm glad I don't have to remember that whole part number. It's written down there for me. So, in our application, we've got this extremely high voltage on one side, and we need to step down to a usable voltage on the other. So, talk to me about how we do DC to DC conversion with these high currents we're dealing with.
So the DC-DC converter is a very important part of the electric vehicle. For example, in a 48-volt converter, you could be talking about 3 kilowatts being used to drive different loads within the vehicle, be it air conditioning, start-stop function, or driving other functions like fans, motors, pumps, etc. So there's quite a lot of energy there. You're at a 48 volt, you could be talking about a couple of hundred amps. So you need a converter. Typically it would be a bidirectional converter. So from 48 volts to 12 volts or vice versa, 12 volts to 48 volts. And that would consist of a buck type stage or a buck boost type topology with synchronous rectification. So you're only using ultra low current MOSFETs to do this. And very often as well, in order to handle the high amounts of current, you would use a multi-phase converter. So instead of having just one energy storage device like an inductor on the output side, you would have two operating slightly out of phase with the currents then combining on the output filter capacitor. And those inductors would have to have some features. They would need to be able to have a very low DCR or DC resistance of the inductor coil. They also would want to have a very low AC resistance as well, which is generated by the AC currents traveling at a high frequency through the coil. And AC resistance is also severely affected by the position of the coil within the inductor. Depending on how close the inductor is or the coil is to the gap of the inductor, you can have fringe fluxing. And that fringe flux can increase the AC resistance of the coil quite significantly, and that can increase losses. So the design of the inductor in terms of the mechanical part of the inductor is very important for reliable operation in these types of applications. And the quality of the inductor is very important as well. So the manufacturing of it has to be highly automated. in order to meet very strict quality standards by automotive customers.
So, focusing in on the inductor part, do we have heat issues we have to deal with there?
Yes, indeed. You're talking when you've got a very high currents going through it, the DC resistance of the wire is very important. And as well as that, as I mentioned, the AC resistance, if it gets too high, can generate quite a significant amount of heat, and that causes the inductor to increase. And as we know from Arrhenius, every 10-degree rise in temperature halves the lifetime of a component. So every degree is very, very important. Typically, what we would do in Bourns is we do quite a lot of analysis using tools like ANSYS for finite element analysis of our inductors, making sure that the AC resistance is within spec on the coil and the flux density inside the core doesn't get excessive. This is very important before we actually make a new inductor, design a new inductor for an automotive application. A lot of simulation is done before we make any samples.
So, inductors is what I've always known Bourns for, in addition to potentiometers. So, tell us about the inductors you've got.
Well, for battery DC-DC converters, currents are very, very high. So what you want is a series of inductors that are able to handle those currents. So in Bourns, we have a series of inductors called the PQ series, and we call them the PQ series because they use a PQ-shaped ferrite core. And this ferrite core is a high-frequency material, so it can operate at high frequencies and has minimized core losses. And we're using a very high-grade stamped copper windings as well, as flat as possible to minimize AC losses. And because it's as wide as possible as well, we're able to ensure that the overall resistance of those coils is less than 1 milliohm. And we manufacture those inductors in an IATF-approved facility on a fully automatic line. So we're making sure that the repeatability of our process meets automotive standards. So these inductors could be used in a multi-phase converter. So if each inductor is using 30 amps, a couple of those inductors in series will help conduct the current that's needed to generate the power required for the 48-volt converter.
Wow, that is quite a beautiful inductor. We may have to mount those on the outside of the vehicle, like we used to do with chrome tailpipes.
Absolutely, absolutely.
Okay, I'm ready to get started, and I'm going to click on that link and go to a Mouser.com page and start looking for my BMS components. But what kind of resources are available for me?
So you can go and click on the link. We've got some white papers on battery management systems and current sensing as well, which gives some more information on our transformers, where they're applied, how to use our current sense resistors as well, how to actually interface with them. And you can also click on the Mouser page for information on Bourns inductors, our shunt resistors, and our TVS diodes, and our circuit protection as well.
Great. I think I'll get a couple of those inductors just to hang on my wall. Well, Cathal, I think that's all I have time for today. Thank you so much for joining me. It was a pleasure speaking with you.
Thank you, Amelia. It was a pleasure as well. Thank you very much.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Bourns. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. Can't miss it, right across the top. Or head on over to YouTube. Keyword EE Journal.